Welcome to this third lecture of EE404 of this week. In the last lecture, we have seen the so-called describing function analysis, and we have applied it to a basic system that is called van der Pol Oscillator. In this lecture, I would like to show you some simulation results for the quantities, amplitude of the oscillation and the frequency of oscillation of the van der Pol Oscillator. And at the end of the lecture, I would like to show you also the simulation results for another system that is called Lorenz Attractor. And we are going to see that Lorenz Attractor is a system for which the so-called Poincare-Bendixson theorem actually does not hold. But the first thing is going to be the so-called van der Pol Oscillator simulation results. So remember the van der Pol Oscillator equations, y double dot plus mu, I have y square minus 1 y dot plus y is equal to 0. Now I have written the van der Pol differential equation for the variable y because I am going to use the variable x for the state definition. Okay? So I would like to solve this differential equation in MATLAB, and this is an ordinary differential equation because there are only derivatives with respect to time in this differential equation, and that makes it an ordinary differential equation. If we had other derivatives like position derivatives, etc., x, y, z derivatives, then this would have been a partial differential equation, but it's not. So we are going to solve this ordinary differential equation in MATLAB using numerical tools. I am not sure how many of you have solved an ordinary differential equation in MATLAB before. In this lecture, I would like to explain the basic methodology to be able to do that. In MATLAB, if you would like to solve an ordinary differential equation, you need to use the so-called ODE functions. ODE is the abbreviation of ordinary differential equation. And there are many ODE solvers in MATLAB. For example, ODE45 is one of these. There are also other ODE different numbers of solvers. And this ODE function takes three different inputs. The first input is the so-called function f. So in MATLAB, in order to be able to solve a differential equation, you need to bring your differential equation into this form. X dot is equal to f of tx. Okay? So you need to bring your differential equation into state space form. And the first argument of the ODE function is this right-hand side of that differential equation, which is the function f. Okay? So here, this t it means that if you want to solve the time-varying differential equation, where the coefficients here might be dependent explicitly on time t, then you use this input t there. And the second input of the f function should be just x. Okay, that is the state. So here, let me try to bring this van der Pol oscillator into this form. In order to be able to do that, I will pass the van der Pol differential equation into state space form. So I will define my state as follows. I have x1, x2, and that is going to be just x1 I will choose as y, and x2 I will choose as y dot. The basic methodology that we have seen in the past. So then I am going to write the state equations. X1 dot is equal to x1 is y, x1 dot is y dot, which is just x2. Well, this is my first state equation. And x2 dot is going to be just y double dot. And I can write y double dot using the van der Pol oscillator equation as minus mu. Instead of y square, I will write x1 square minus 1. And instead of y dot, I will write x2 and minus y, which is x1. Okay? So this is the state space form of my van der Pol differential equation. All right? So this f function is just an implementation of the right-hand side. So the f function outputs this x out, the right-hand side of this differential equation, and you need to, so this is in MATLAB, so this is x out, you need to write a function f which takes t, and it needs to take also x. Okay, the first element of x is just x1. In this case, we are going to select x two-dimensional. Okay, because we have a second order system here, and this function x is going to get t values, and it's going to get x values, and it's going to return the right-hand side here, x out. All right. So let us say that we take the first row element of x. I will call this as x1. Let us say that in MATLAB I have taken the first row of this x input. x2 is going to be the second row of the x input. And then I will return this x out as follows. X out, the first row is going to be x2. And I will go into the second row here, and of course I need to define a mu here. So in this function I need to know what mu is. Let us say that I define a mu here, variable, which is 3 here. Okay, and then I will write here the second row of this output, which is going to be minus mu times x1 square. x1, I will take the square of this array, I will subtract 1, and then I will multiply it with x2 array, and then I will subtract x1 from it. So here the reason that I think about this x1 and x2 as arrays is that MATLAB usually evaluates this f function at multiple x values at the same time. So in general, this small x variable input by the MATLAB becomes an array, okay, and each column contains a different x values, x1 and x2 values. So here I take the first row as the x1 variable and the second row as the x2 variable, and I set mu here, and then I write the right hand side here. MATLAB works by running this function for different t and for different x arrays. All right, but here all you have to do is to actually calculate the right hand side here. Sorry, there is a screensaver here. So here let me show you my f function. So it is very similar as I showed you. So this is, I read the x1 values in the first row, and I read the x2 values from the second row, and I set mu equals to 1. Here I set mu equals to 1. And then the output becomes, the first row of the output is x2, and the second row of the output is given by the right hand side here. Okay? So that is my f function, and MATLAB's ODE45 function, actually all ODE functions, they take first a pointer to this function f that you have written. Okay, so this f is the name of the file that you store that function. Okay, and if you just write @f here, this gives the function ODE45 the pointer of that function, so that MATLAB can actually call that function while it's trying to solve the ordinary differential equation, and it can evaluate that function at different values in the state space. So the second input to the ODE function is the time instance that you would like to solve the differential equation at. So obviously the solution of a differential equation like this is going to be a function of time. So we would like to find what x of t is, and what x of t means that I need to find an array of x values, x1 and x2, at different time instants. Time equals to 0, time equals to 1.5. If whatever time values I would require the solution at. Okay? So then you give the MATLAB the list of time values that you would like the solution to be given to you at. Okay? And I have given here the required time values as some initial time and at some final time, and I have taken 10 samples there. These 10 samples would be really too few samples. So I have just done this in order to be able to give an example. In the other parts of this course, in the other parts of this code, I am actually solving this differential equation at a much frequent samples. Okay. So I would I solve this differential equation piece by piece for different time instance in the for loop that is coming soon. So this first comment is just an example here. I do the actual solving in the future parts of this code. So the third input of the ODE function is the initial condition that you want to solve the differential equation for. Of course, in order to be able to, so here you see that although this function f contained this t input, I did not use it because here the differential equation that I would like to solve, these equations are in the form f of x. So the right hand side here does not depend on t explicitly. If the right hand side depended on t explicitly, like this for example, if there was a t here, then I would use this t input as well, but in my f function. But here, since my right hand side is just like this in this differential equation, we have an autonomous system in this case. I did not use this t input, but still the f function should be written for two inputs, t and x. And if your right hand side is independent of time, then you are not going to use it inside. So the second input is the time instance that you want the solution at, and the third input to ODE function is the initial condition. Whatever initial condition of the state that you would like to solve the differential equation at. Okay? So then you give a vector with two elements there. So here I have chosen my initial condition at the point 1, 1. x1 is 1 and x2 is 1. And I gave this to the function. So if I now run this part of this code, so I would just see, I will show this later. So let us stop it here. So let me just come to this point. Okay? So if I run the code a single step, then these are, and the ODE function gives you these outputs. So these t output values, these are the input values that you wanted the solution at, and the x values that you get. So you would get an array here. Then at each t value, for example, at t is equal to 0, we have our initial condition, 1, 1. At t is equal to 11.1111, we would have the solution minus 1.44 and 0.82. Okay? So the MATLAB just solved the differential equation at the times that you have requested. Okay? So now, this was just an example code. Then what I did in the following, I will share this code with you. What I did in the following is that I have solved this differential equation step by step at different intervals, and I have connected those intervals together to show you a simulation that shows the trajectory in the phase plane. for this one dipole oscillator. Remember that we have applied the so-called describing function analysis to this one dipole oscillator differential equation, and we have found the oscillation parameters here, which was we have found the oscillation frequency, omega is equal to 1 radians per second, and this corresponded to a period of 6.28 approximately seconds. Okay? And the oscillation amplitude, this is the oscillation amplitude of y here, and that is going to be, that has turned out to be plus minus 2 here. Okay? So now we are actually ready to run this. So this is the solution. I hope it is visible in the. So I'm solving the differential equation step by step, and these green values, they are the solutions for the last time. And this was the initial condition, which was 1, 1. And you see that after that point, the system converged to a stable oscillation. Let me run it once more, maybe with some other initial condition. So let me change the initial condition to 1, 5. Let us see what it is going to do in that case. So I have changed the initial condition and solved it again. So we see that wherever I start with the initial condition, the system trajectories would actually converge to an oscillation. And here x-axis is x1 and y-axis is x2. And now look at the limits of the oscillation here. Maybe I should have thought about this before. Now look at the oscillation limits here. So you see that I have minus 2 and plus 2. So x1 is changing between minus 2 and plus 2, and that is basically the magnitude of the oscillation. The oscillation is not purely sinusoidal here, and you can see this in this figure. So that is how x1 is changing during the simulation, and that is how x2 is changing. X1 is the derivative of x2 is the derivative of x1, and here we see that the oscillation is not purely sinusoidal, but in the describing function analysis we have assumed that the oscillation is purely sinusoidal, and in any way we have estimated the magnitude of the oscillation at plus minus 2. So you see that this is quite accurate here. And what about the period of oscillations? Here, if I zoom a little bit here into this part, so you can just look at how much time is between the two dips here. So you see that it is approximately 6 seconds. All right. So you see that although the method is quite approximate, it can give you quite accurate results. So remember that these results were independent of mu. So we have seen in the describing function analysis that this amplitude was independent of mu. Furthermore, this frequency was independent of mu, frequency and period. So here, I might wonder about if this is true in reality. So in the simulations, as you might remember, in my f function, I have selected mu equals to 1. So I can just choose another mu value and try to see if these results are really independent of the mu value. So I select mu equals to 3 and run it once more. So now if I look at the x1 limits of the oscillation, I would still see minus 2 plus 2. So that is pretty good. But you see that the oscillation actually differed from a circular type of oscillation a lot. So the sinusoidal structure was disturbed by the increase of this mu parameter. And when I look at x1, it is less sinusoidal now. And what about the period of oscillation in this case? So we see here that it is actually, maybe I should concentrate on here. So this is like 22.5, and I have 31.5. So it is approximately 9 seconds. So you see the approximation in this method. The E hat, the amplitude of the oscillation, really did not change when I change mu. So the amplitude was quite accurate, but you see that the mu in reality, the frequency of oscillation in reality is dependent on mu a lot. So when I changed mu from 1 to 3, then the frequency of oscillation changed, but the describing function analysis could not actually predict that type of change. Okay? So you need to keep in mind that this describing function analysis is an approximate method, and there is no guarantee that these results are going to hold in reality. So here, for example, it could not predict the change of this period of oscillation with respect to the mu parameter. Okay? So I will share this code with you in OptiClass, and you can actually play with it. So you can give different system equations to the function f, and you can see their phase plane trajectories yourself. So now in the second part of this lecture, I would like to give you a system, a third order system, for which the Poincaré-Bendixson theorem, it's the last theorem that we have seen in the parts of the course related to the results about the non-existence and existence of periodic trajectories. And this system is called Lorenz Attractor. And it is a very, very famous system because when people discovered this system, it became the start of the so-called chaos theory. Okay? It's modeling a meteorological system. So it's a model of the weather. So I have sigma x1 minus sigma x2. x2 dot, as I told you, it is a three-dimensional system, and therefore it has three state variables: rho x1 minus x1 x3 minus x2. x3 dot is equal to x1 x2 minus beta x3. So these are the state equations of the three-dimensional Lorenz attractor. So do you think the Poincaré-Bendixson theorem, can you question that Poincaré-Bendixson theorem would hold or not for such a system? The nonlinearities are really quite simple, just some multiplicative nonlinearities here. But the reason that Poincaré-Bendixson theorem does not hold for such system is that it's third order. So chaos theory or chaotic behavior starts from the third order for continuous time systems. So, and Poincaré-Bendixson's theorem just tells us that for a second order system, the chaotic behavior cannot occur. And here we have a third order system, so just from the start, Poincaré-Bendixson's theorem would not be valid. So the implementation for this example is really very, very similar. So I have a three-dimensional state in this case. So you see that I have x1, x2, x3, and I just select some parameters here for which the chaotic behavior would be seen. And the right-hand side of the equation x dot is equal to f of x is given by these equations. Okay? So now I have again, in this time I gave the system an initial condition which is x0 equals to 3, 2, 1, and then I would plot the results just. So this figure is a very, very famous figure of the trajectories of the Lorenz attractor. So you would see that the trajectories would never leave this rectangular region here. They always remain in a bounded region forever. And it is known that when you look at the equilibrium points of the system, in this region, there are actually no equilibrium points at all. So the trajectories of the Lorenz attractor, they would remain in a bounded region, in a finite region forever, where there exists no equilibrium points inside. All right? So what does Poincaré-Bendixsen's theorem tell us? For a second order system, if the trajectories would remain in a bounded region, then in which no equilibrium points exist, then the trajectory should either go to a stable periodic trajectory or it should be itself a periodic trajectory. It can be actually proven that these trajectories of this Poincaré-Bendixsen's theorem, they are never periodic. It looks like they are periodic from such figures, but they are actually not periodic. So let me restart it once more. So they start and they make this famous butterfly shape, and you can actually prove that. I don't know about the proof, but it is well known that a trajectory of a Lorenz attractor never passes a point that it has passed in the past. Okay, so therefore these trajectories are never periodic, and it is actually very, very difficult to predict the behavior of such trajectories. Actually, so here we see a system, a third order system, whose trajectories remain in a bounded finite region where no equilibrium points exist, and the trajectories are neither going to some periodic trajectories, nor they are actually periodic trajectories. Okay, so that example is the violation of a Poincaré-Bendixsen's theorem, but it is really expected because this is a third order system for which that theorem does not hold. Okay. So now what I would like to show you is the following. I would like to show you these trajectories separately. So here, of course, that was a three-dimensional trajectory. So it has an x component, y component, and z component. Now I would like to draw you those x, y, z components separately. All right? So now I will comment this part out. And I will uncomment these parts. So now this is how those trajectories would be looking like in different dimensions. I have the x coordinate, y coordinate, and z coordinate. This is the same trajectory starting from the initial condition that I have given. Now, after I draw this trajectory, I would like to show you something very interesting, and that is actually what chaos theory is. Chaos theory means that there are some systems, and these systems are really incredibly sensitive to their initial conditions. So if I have a linear system, if I perturb the initial condition of a linear system, then if I draw the trajectory of the system for the actual initial condition and the perturbed initial condition, I would actually see that they would be very close to each other. But we are going to see that now, after plotting this, I am going to change the initial conditions of the system just a little bit, okay? And then we are going to observe the new trajectory of the system with those perturbed, slightly perturbed initial conditions, right? So here, my original initial condition that I have drawn these x, y, z values is my original initial condition is 3, 2, and 1. So x starts at 3, y starts at 2, and z starts at 1. Now I'm going to change this initial condition just a little bit, all right? So I make the second initial condition, I change it from 2.0 to 2.1, okay? And then I'm going to draw the new trajectory with a new color. So I will again choose the green color here to draw the trajectories. And I will do that drawing on top of this earlier trajectory, okay? So here the thing that you have to realize here is that when I perturb the initial condition just a little bit, if it was a linear system, I wouldn't have seen any difference with this type of scale in the trajectories. So when I change the initial condition, I would have seen for a linear, if this was a linear system, I would have seen, or if this was a non-chaotic system, I would have seen a trajectory exactly on top of this old trajectory after the perturbation of the initial condition. Here there is going to be a difference actually, and that difference is the surprising part of chaotic systems. So I have changed the initial condition, and now I can draw trajectory once more. So you see that at first the new trajectory is almost on top of the earlier trajectory, okay? But that is not going to be the case forever. So you realize that something changed now, okay? So, and now it is completely different. It's making something completely different now. So this is called the sensitivity of this type of systems to their initial conditions. In order to be able to predict the trajectories to a far distance in time, then you need to know your initial conditions very, very accurately, okay? Even small changes in the initial conditions can make infinitely large differences in the future in your predictions. That is, so this is modeling a weather system. So if you would like to predict the position of the clouds, or when it is going to rain and when it's going to snow, etc., you need to use this type of models with weather radar measurements. But if you do not know your initial conditions extremely accurately, your predictions are going to be valid only for the near future, okay? Because these type of systems are chaotic, they are very, very sensitive to initial conditions, and even a slight change, even a negligible change in the initial conditions can make actually very, very large differences in the far future. Okay? That is why we cannot actually predict the weather accurately for very, very long time periods. And actually this type of behavior is called, as you might have all heard, it is called the butterfly effect. Okay? So tiny changes in the air system which is caused by the wings of a butterfly can cause a tornado in the future, because it's changing the initial conditions and it's going to result in very, very different far future at the end. Okay? So this was just an illustration of the Lorenz attractor. I will also share this code so that you can examine. So I'm also giving this code because you might want to try different dynamics and try to observe. So you might change these f functions, and you might look at the phase plane trajectories for different systems yourself. And you can actually try to validate the results that we have obtained for drawing phase plane trajectories in the class. So I'm actually going to finish this lecture here, and this finishes the lectures of this week. Thank you very much for watching. Bye.